Hello guys, welcome on Tesla Adventures. In this video, we are going to start the solutions of test number 5, which is of thermodynamics. So in this first question, you can see that there are two graphs which shows the variation of temperature of the two bodies X and Y, which are they are having same area and they are cooling down by the emissions of radiations. So we have to find out the correct relationship between emissivity and absorptivity of the bodies. So we know that obviously the rate of change of temperature with time is greater for X and is less for Y, because graph of X is decaying very steeply. So we can say that the power which is being lost by the two bodies is greater for X and less for Y. So we can say obviously that the emissivity of X would be greater than emissivity of Y, and the other thing is about absorptivity. So we know that according to Kirchhoff law, absorptivity is directly proportional to the emissivity. So obviously the absorptivity of A of X would be greater than the absorptivity of Y. So the correct option for this is option C. Now we move on the next question. In this question, you can see that there are two elastic rods which are joined together, and they are being fixed between two rigid supports. And if there is no change of the length of these two rods, which means that if this junction does not shift on increasing the temperature, then we have to find out the correct relationship, where obviously alpha 1 alpha 2 are the linear expansion coefficients of the rods, a1 a2 are the area of cross sections of the rods, and gamma 1 gamma 2 are the Young modulus. So I have already drawn the diagram on this page. So you can see that this is the original position of the junction, and let us suppose that junction has shifted. So we know that if junction has shifted towards this side by a distance of X, so we assume that if this rod was alone, then it would have shifted by a distance of delta L1, and delta L1 is the change in length due to thermal expansion. So that would be equal to L1 into alpha 1 delta T, and similarly delta 2 will be equal to L2 into alpha 2 delta T. I'll write it down here. Delta L2 will be L2 alpha 2 delta T. Now we have assumed that if this rod was not present, then it would have expanded freely, but due to the presence of this rod, this will be the restricted length. Now restricted length is obviously the length which is suppressed by this rod. Okay, so this length would be delta L1 minus X. You can also refer this video in detail for in the playlist of elasticity. So this would be the restricted length, and restricted length would be delta L1 minus X. So the stress developed in the first rod would be delta L1 minus X divided by original length L1, and this would be equal to this is strain in fact, and this would be equal to stress upon area into Young's modulus, which is gamma 1. And similarly the strain developed in this rod will be the restricted length upon original length. So you can see that if this rod was alone, it would have expanded from this position, in fact from this position to this position, by a length of delta L2. But due to presence of this bigger rod, this rod has been compressed by a distance of X in the reverse direction. So restricted length would be delta L2 plus X obviously. So this is delta L2 plus X upon the original length is L1, and this would be equal to F upon A into gamma 2, A to gamma 2. Now we know that if there is no shift in the junction, therefore X is 0, and also we know that force applied would be same. So we can equate F. So we can see that delta L1 would be L1 alpha 1 delta T divided by L1. Now we know that x is 0 if junction is not shifting, therefore we can substitute x is equal to 0, and we can substitute the value of delta L1 and delta L2, and we can equate the value of f. So we can see that it would be alpha 1 delta t into a1 gamma 1 will be equal to alpha 2 delta t into a2 gamma 2. So cancelling delta t with t, we can see that a1 by a2 will be equal to alpha 2 gamma 2 divided by alpha 1 gamma 1. So this D is the correct answer. Now we move on the next question. In this question, you can see that there is a composite slab which is made up of two different materials. The temperature on the outermost surfaces is T2 and T1, and it is given that T2 is greater than T1. The thermal coefficient of conductivity is 2K for this slab and K for this slab. So we have to find out the rate at which heat is transferred from this point to this point. So first of all, let us see that if the resistance of this slab is R1 and the resistance of this slab is R2, so R1 will be equal to this length, you can see complete length will be equal to 4x, so and this length is x, so R1 will be equal to x upon conductivity K into area of cross section is, let's suppose, A, and this is R. We are assuming that this is R, so R2 will be equal to the length of the slab is 4x upon K is 2K, and the area of cross section is same, so you can see that this would be 2R, and therefore in series the equivalent resistance would be equal to 3R. So R equivalent will be equal to 3x by Ka. And now we know that this rate at which heat is transferred is dq by dt will be equal to delta T upon R equivalent, and delta T is T2 minus T1, and R equivalent is 3x upon Ka. So the value of F will be equal to 1 by 3. So the correct answer is D. Now we move on the next question. In this question, you can see that there is an ideal gas and it is going through a process PV to the power n is equal to constant, where P initial and V initial are the initial pressure and volume of the gas, and V final is the final volume of the gas. So we have to find out that in which case the work done by the gas would be minimum. So we know that the general formula for the work done is nR delta T upon gamma minus 1 for any polytropic process. But we will not solve this question through this formula. In fact, we will use the graph analogy. We know that if PV is constant, which means n is 1, then it is isothermal process, and in isothermal process the graph would be like that. This is V initial and this is V final. Okay, and if n is equal to gamma, so it is PV to the power gamma is equal to constant. So it is adiabatic process, so graph would be like that. And if this power is 1 by gamma, n is 1 by gamma, so we know that y is proportional to 1 by x is hyperbola, and y is proportional to 1 by x square is also hyperbola, but it is deeper hyperbola. So as we will increase this power, the hyperbola will become steep and deeper. So we know that obviously gamma is obviously greater than 1. So 1 by gamma would be less than 1. So this first graph represents n is equal to 1. This second graph represents n is equal to 1 by gamma. And the third graph is obviously isothermal graph. So this is n is equal to gamma. And if n is equal to 0, so P is constant. So this is isobaric process. So this would be like that. Okay, so this is these are the 4 graphs. So you can see that the minimum area is the minimum work done, and the minimum area is in the case when there is adiabatic process. So it is work done would be minimum for n is equal to gamma. So the correct answer is A. Now we move on the next question. In this question, you can see that there is a uniform cylinder of steel whose mass is m. Its radius is r, and this is placed on a frictionless bearing, and it is set to rotate about the vertical axis with the angular velocity of omega naught. After this cylinder has reached the specific state of rotation, it is heated without any mechanical contact, and its temperature is increased from T0 to T0 plus delta T. So if delta I by I is the fractional change in moment of inertia of the cylinder, delta omega by omega naught is the fractional change in angular velocity of the cylinder, and the fractional change in angular velocity is delta omega naught by omega naught, and alpha is the coefficient of linear expansion. So we have to choose the correct option. So we know that moment of inertia is mr square. So if we differentiate this equation, then di will be equal to 2mr into dr. Okay, and if we divide these two equations, then di by I will be equal to this is cancelling mr, so it is 2 dr by r. So we can say that the one of the correct option is A. And the second thing is the fact that omega is the angular velocity. Now we know that moment of inertia I into omega is angular momentum, and if we heat up this body, then obviously angular momentum will remain unchanged. So we can say that the moment of inertia is inversely proportional to omega. Okay, so if this will increase, then this omega will decrease. So we can say that delta I by I will be equal to minus of delta omega by omega naught. And obviously delta omega naught by omega naught will be equal to minus of 2 delta I by I, and delta I by I is dr. This 2 is from here only, so it would be minus of 2 dr by r, and dr by r will be alpha delta t. So C is also correct. So the correct options are A and C. Now we move on the next question. In this question, you can see that there is a dark room whose ambient temperature is T0, and there is a black body which is kept in that dark room. The temperature of the black body is T, and keeping the same temperature of the black body, sun rays are allowed to fall on the black body through a hole in the roof of the dark room. And assuming that there is no change in the ambient temperature of the room, which of the following statement is correct? So we know, first of all, we see that in option A, it is given that the quantity of radiation absorbed by the black body in the unit time will increase. Obviously, black body absorbs all the radiations incident on it. So if extra radiations from sunlight are incident on the black body, then it would absorb them all, and therefore the amount of radiations absorbed by the black body in unit time will increase. So option A is correct one. Now we know that emissivity and absorptivity are equal for the black body, hence the quantity of radiations emitted by the black body in the unit time will also increase. This is also correct. And black body radiates more energy in the visible spectrum. See, the energy absorbed by the black body, additional energy absorbed by the black body is due to the sunlight, and obviously it is in the visible spectrum. Therefore the black body will radiate the visible spectrum radiations, and hence C is also correct. And the reflected energy in the unit time by the black body remains the same. We know that the reflectivity of the black body is 0, so the reflected energy by the black body in the unit time will be 0, and it would be same throughout. So the correct answers are A, B, C and D. Now we move on the next question. In this question you can see that during an experiment an ideal gas is found to obey the condition of P square by rho is equal to constant, where rho is the density of the gas and P is the pressure. The gas is initially at the temperature T and the pressure P, and density of the gas initially is rho. If the gas expands in such a way such that its density becomes rho by 2, then we have to choose the correct option. First of all, let us see that density rho is equal to mass upon volume, and if the process equation is P square by rho is equal to constant, then we can say that P square by m into V is equal to constant. Now mass of the gas will remain constant throughout, so we can say that the process equation will be P square V is equal to constant. Okay, and if the density becomes half, then it means that volume will become twice. So we can say that P square V, P1, in fact initial pressure is P obviously, so final is, let's suppose, PF, and the volume is twice 2V, so P final will be equal to P divided by 2, and there would be a root. So option A is wrong. The temperature of the gas. Now let us talk about the temperature. So if P square V is constant, so we can say that out of P square V, PV is nRT, so nRT into P is constant, therefore Tp is constant, and we know that pressure has become 1 upon root 2 times, so we can say that the initial pressure is P, initial temperature is T, final pressure is P upon root 2, and final temperature is Tf, so Tf is equal to root 2T. So this is correct, B option is correct. Now the graph of the above process on PT diagram is a parabola. So this PT diagram, PT graph would be a hyperbola because it is an inverse relationship. So this is wrong, and the graph of the above process on PT diagram is hyperbola. So it is correct. So the correct answers are B and D. Now we move on the next question. In this question, you can see that there are two plots between ln P and ln V, where P is pressure, V is volume, for two different gases X and Y having degree of freedom F1, F2 and molar heat capacities at constant volume CV1, CV2. And these plots are being plotted for adiabatic process. So we have to choose the correct one. So first of all, let us see that PV to the power gamma is equal to constant. This is the equation of adiabatic process. And if we take log both sides, then we can say that ln PV to the power gamma is equal to log of constant is also constant, and ln this is ln P into ln P plus gamma ln V, this is C. So ln P is equal to C minus gamma ln V, and you can see that this is the equation of a straight line. This is y, and this is x, and this is slope. Okay, and you can also see that slope of x is greater than slope of y. So slope is actually the gamma, and uh, gamma of x is greater than gamma of y, and we know that gamma is equal to 1 plus 2 by f. So gamma is inversely proportional to the degree of freedom. So we can say that degree of freedom of x is less than degree of freedom of y. Okay, so the correct option will be B, as well as we also know that CV is R upon gamma minus 1. So CV of second will be greater than CV of 1. So the correct answers are B and C. Now we move on the next question. In this question, you can see that we have to choose the correct option. So for an ideal gas, the change in internal energy in a constant pressure process from temperature T1 to T2 is equal to NCV T2 minus T1, where CV is the molar specific heat at constant volume and N is the number of moles of the gas. So this is absolutely correct. We know that in any process apart from that isothermal process, the change in internal energy is NCV delta T. Now the change in internal energy for the gas and the work done by the gas are equal in magnitude for adiabatic process. Obviously, we know that for adiabatic process dQ is 0. So du is equal to minus dW, which means that the change in internal energy and the work done are equal in magnitude. So B is also correct. The internal energy does not change in isothermal process, obviously, because in isothermal process temperature remains constant and there is no heat is added or removed in an adiabatic process, obviously, because we know that adiabatic process does not in adiabatic process gas does not exchange any heat with the surroundings. So the correct answer of this question are A, B, C, D. Now we move on the next question. In this question, you can see that there is a gaseous mixture that contains equal number of moles of two ideal gases having adiabatic exponents gamma 1, gamma 2, and the molar specific heat of the gases at constant volume is CV1 and CV2 respectively. So we have to find out that which of the following statement is correct. The first statement is the adiabatic exponent of the gaseous mixture is gamma 1 plus gamma 2 by 2. We know that the gamma of the mixture, let us first of all write down that gamma of the mixture is equal to N1 gamma 1, in fact N1 Cp1 plus N2 Cp2 upon N1 Cv1 plus N2 Cv2, and N1 and N2 are equal. So gamma is not gamma 1 plus gamma 2 by 2. So A option is incorrect. Now the molar specific heat at constant volume. So Cv mixture is equal to N1 Cv1 plus N2 Cv2 upon N1 plus N2. So if N1 is equal to N2, so Cv mixture is equal to Cv1 plus Cv2 by 2. Okay, so B option is correct. And molar specific heat at constant pressure for the gaseous mixture. So Cp is Cv mixture, Cp mixture is Cv mixture plus R. So Cp mixture is equal to Cv1 plus Cv2 by 2 and plus R. So C option is also incorrect. And adiabatic exponent for the gaseous mixture is this. So what we can do, we can write down Cv mixture as R upon gamma minus 1 So gamma minus 1 is equal to R upon CV mixture. Let us write down on the next page. We know that CV mixture will be R upon gamma minus 1, and gamma minus 1 will be equal to R upon CV mixture, and gamma will be equal to R upon CV mixture plus 1. So gamma will be equal to R upon CV mixture. Now CV mixture is equal to CV1 plus CV2 by 2. So this is CV1 plus CV2 by 2 plus 1. So D is also correct. So the correct answers are B and D. Now we move on the next question. In this question, you can see that there is a long container and there is some air enclosed in the container in between these two pistons. The air is initially at the room temperature and at the atmospheric pressure of 10 to the power 5 pascals, and the volume of air trapped in between these two pistons is 20,000 cc. The area of cross section of the piston is 100 centimeter square, and the force constant of the spring is 100 Newton per meter. If we push this piston right at the place of this piston isothermally and slowly, and it reaches at the place of this piston 1. So we have to find out the final length of the gas or the air in the cylinder, and we have to assume that initially the spring was relaxed. So obviously we know that the initial pressure of the gas was 10 to the power 5 pascals. The initial volume of the gas is 20,000 cc. Now this is 20,000 cc, and if we convert it into standard unit, then it would be into 10 to the power minus 6. So it would be 2 into 10 raised to power minus 2 meter cube. Okay, and this distance is, let's suppose, L, length of the gas column initially. So L will be equal to volume upon area. So L is equal to 200 centimeter. So it is 2 meters initial length. And now what we have done, we have isothermally pushed this piston 2 till it reaches the position of piston 1. So in this process we have compressed the gas and we have also compressed the spring. So now what we should do, that if this process is isothermal and we know that the final pressure will be the atmospheric pressure which would be acting on this piston from outside plus spring force divided by area. So atmospheric pressure is 10 to the power 5 plus spring force is kx divided by area, and the final volume will be equal to the initial volume plus the additional length this piston has moved out. So we are assuming that this piston moves out by a distance of x. So the increase in volume would be x into area, and if this piston moves in towards this side by a distance of 2 meter, so the decrease in volume will be minus of 2 into the area. Okay, so you can see that initial volume and this would be cancelled out, and we can apply P initial V initial, that is equal to P final V final. So P initial is 10 to the power 5 and V initial is 2 into 10 to the power minus 2, and P final is 10 to the power 5 plus K, which is 10 to the power 3, X is X, area is 10 to the power minus 2 in meter squares, multiplied by X into A, X into area is 10 to the power minus 2. So you can see that 10 to the power 5 is cancelled out. So this is 2 into 10 raised to power minus 2 is equal to 1 plus x into 10 raised to power minus 2. Cancelling this. So equation is x into x plus 1 is 2. So obviously x is equal to 1. So the correct answer of x is equal to 1 meter. Now we move on the next question. In this question, you can see that there is a cubical box of side 1 meter. So let us draw a cubical box. This is a cubical box of side 1 meter, and in this box there is a helium gas whose atomic weight is obviously 4, and the pressure of the gas is 100 Newton per meter square. We are observing a single atom which is traveling with the root mean square speed, and we are observing that atom in the time span of 1 second. We observed that that atom was found to make 500 hits on the single wall, so without any collision with the other atoms. We have to find out the temperature of the gas. So let us assume that this atom hits this wall 500 times in a single second. So to hit this wall again, it has to move a distance of 2 meters. So let us assume that the speed VRMS, speed V, will be equal to the total distance traveled. So in one collision the distance traveled is 2 meters. So in 500 collisions it would be 500 into 2 divided by the time is 1 second. So VRMS is equal to 1000, and we know that VRMS is under root 3 RT by M, and this is 10 to the power 6 into M. I am squaring both the sides. So into M is 4 into 10 raised to power minus 3. You have to remember that M is in grams, so you have to take it in kilograms. Divided by 3 into 25 by 3 into, now we have to find out the time, in fact temperature. So this temperature would be 160 kelvins. So the correct answer is 160. Now we move on the next question. In this question, you can see that there is a mercury barometer, which is a vertical tube whose one end is open, and the open end is being dipped into the mercury, and the other end is closed, which is outside the mercury. So this mercury barometer initially is being dipped into mercury, and the air trapped above the level of mercury has a length of 60 mm, and the mercury level in the barometer is 740 mm. Now we have suppressed this barometer down in the mercury. So we observe that the mercury level becomes 730 mm, while the air trapped in it becomes 40 mm. So now we have to find out the true pressure of atmosphere in terms of mm of Hg. So let us assume that the initial pressure of the air inside this inside this barometer is P1, and inside this barometer is P2. So we know that P1 plus 740 rho g, rho is density of mercury, is equal to P2, P naught, and in the second case P2 plus 730 rho g is equal to P naught. Okay, what we are doing, we are equating the pressure at these 2 points. Now we also know that P1 V1 is equal to P2 V2, because these processes are isothermal, and we can eliminate area of cross section both the sides. So P1 L1 is equal to P2 L2. Now P1 is P1 and L1 is 60, P2 is P2 and L2 is 40. So P2 is equal to 3 by 2 P1. So substituting this value in this equation, so this is 3 by 2 P1 plus 730 rho g is equal to P naught, and that is equal to P1 plus 740 rho g. So P1 by 2 is equal to 10 rho g, and P1 is equal to 20 rho g. Now we can substitute the value of P1 in the first equation. So we can see that 20 rho g plus 740 rho g is equal to P naught. So the pressure of air is 780 mm. In fact 760 mm of Hg. So we have to report the answer in terms of n plus 80 by 120. So n is 760, so 760 plus 80 by 120 is 840 by 120, which is 7. So the correct answer is 7. Now we move on the next question. In this question, you can see that there are two arrangements of the blocks of different thermal conductivity, and when they are connected in situation A, the temperature difference is maintained between this end and this end. So you can see that they would be heat would be flowing like that, and they would be in series like that. And in this case, the temperature difference is maintained between 3 and 4. So they all would be in parallel because heat would be flowing like that. Okay, so it is given in the question that the equivalent thermal conductivity of the second case is 20% higher than the equivalent thermal conductivity of the first case. We have to find out the number of slabs in the arrangement. So obviously, first of all, let us see that in the first case, it is all the slabs are in series. So R equivalent will be equal to R1 plus R2 up to Rn. And R equivalent will be equal to L by Ka. Now the total length of the system will be equal to L1 plus 2 plus 3 up to N divided by K equivalent into area. Area of cross section of this slab is D square, and it is equal to the sum of other resistances. So the resistance number 1 is L by D square into K. Now the resistance number 2 will be 2L by 2K into D square plus 3L by 3K into D square up to so on. So this is AP, whose first term is A and the common difference is 1. So this is L, and the sum of AP is N by 2 into 2A plus 1. You know the sum of AP, so we are writing it down directly. So this is N by 2 into 2A. 2A is 2 plus N minus 1 into D, it is 1, divided by K equivalent into D square, and it is equal to L by D square K, and this is 1 plus 1 plus 1 n times, so it is n. Okay, so you can cancel out K D square, in fact L D square, L by D square, and you can also cancel out n. So you can see that this will be n plus 1 by 2, and it is equal to 1 by K. So n plus 1 by 2 K equivalent will be equal to 1 by K. So K equivalent 1, let us name it as K equivalent 1, will be equal to K into n plus 1 by 2. Now in the second case, the all slabs are in parallel to each other, and in parallel we know that 1 upon R equivalent 1 upon R equivalent will be equal to 1 upon R1 plus 1 upon R2 up to 1 upon Rn. And in we know that 1 upon R is Ka by L. So you can see that in each case the total area in this case will be this is L into D, this is 2L into D, this is 3L into D. So sum of the area will be, this is K equivalent 2, and sum of the area is L into D plus 2LD plus 3LD and so on, NLD, divided by the length of this combination is the length which is measured in the direction of heat flow. So this length is d, so the length would be d, and it would be equal to 1 upon r1, which is this. So the r1 will be 1 upon r1 will be Ka by L. Now K is K for the first slab, area is L into D, and length is D. So K L into D, length is D. Now for the second slab, K is 2K, length is 2L, so area will be 2L into D. So area will be 2LD divided by length is again D. So this will be 3 square KLD by D, and so on till N. So you can see that it would be again AP, and you can take out LD and you can cancel out D. So K equivalent 2 into L into this AP is 1 plus 2 plus 3. So 1 plus 2 plus 3 up to N is equal to this, taking out this D, cancelling D with D, taking out KL common. So it would be KL 1 plus 2 square plus 3 square up to so on. Okay, and this is, so K equivalent 2 will be equal to K into, you know that this is a series 1 square plus 2 square plus 3 square and so on. The sum of this series will be n into n plus 1 into 2n plus 1 by 6, and divided by sum of this AP. So AP sum will be n by 2 into 2 into 1 plus n minus 1 into D. Now K equivalent 2 will be equal to K by 6 into n plus 1 into 2n plus 1 divided by n by 2 into n plus 1. So cancelling n with n plus 1 with n plus 1, this is 3. So it is equal to K by 3 into 2n plus 1. And it is also given that K equivalent 2 is 20% greater than K equivalent 1. So K equivalent 2 will be equal to K equivalent 1 into 6 by 5, because this is 20% greater. So K by 3 into 2n plus 1 will be equal to 6 by 5 of K equivalent 1, which is K into n plus 1 by 2. So this is K into n plus 1 by 2. So cancelling K with K, this is 3. So 5 into 2n plus 1 will be equal to 9 into n plus 1. So 10 plus 5 is equal to 9n plus 9, and this is 10n. So n will be equal to 4. So there are 4 slabs. So the correct answer of this question will be 4. Now we move on the next question. In this question, you can see that 2 moles of an ideal gas of adiabatic constant 7 by 5 is mixed with the 1 mole of another gas of adiabatic constant 4 by 3. We have to find out the gamma of the mixture. So we know that gamma mixture is equal to N1 Cp1 plus N2 Cp2 divided by N1 Cv1 plus N2 Cv2. Okay, so and we also know that Cp is equal to gamma R upon gamma minus 1, and Cv is equal to R upon gamma minus 1. So let us substitute these values. So gamma mixture will be equal to N1 is 2, Cp1 is 7 by 5 R upon 7 by 5 minus 1, which is 2 by 5, plus N2 is 1, Cp2 is 4 by 3 upon 1 by 3 into R divided by 2 into CV1 is R upon gamma minus 1. Now gamma minus 1 will be 2 by 5. Again, this is N2. N2 is 1, and this is R upon 4 by 3 minus 1, which is 1 by 3. So you can see that this is 7 plus 1, 11R, and this will be 8R. So this is 11 by 8. So alpha will be equal to 8. Now we move on the next question. In this question, you can see that there is some gas whose Cp by Cv is 1.25 and it follows this cycle ABCDA. Now we have to find out the ratio of energy extracted by the gas to surrounding during this isochoric section, and the work done by the gas during expansion during isobaric section. This is isobaric obviously, and this is isochoric. So let us assume that this temperature is T1 and this temperature is T2, and this is V1 and this is V2. So in this process, isochoric process, you can see temperature is decreasing and therefore volume is constant and therefore pressure would decrease. So we have to find out the energy extracted. So work done will be 0 in this process. In process CB, in CB work done will be 0, or BC, you can write down BC. Work done is 0 because volume is constant, so heat extracted will be equal to nR delta T. Now we just have to take the magnitude of delta T because already we have used the sign, as we know that T1 would be less than T2, therefore heat Q will be negative, and negative sign indicates that heat is being extracted. So we are just calling it as extracted heat and we are taking its magnitude. So Q will be equal to N and R, in fact N CV delta T. This is N CV delta T. So N and CV is R upon gamma minus 1. So gamma minus 1 will be 0.25 and this is delta T. Okay, so Q will be equal to 4nR delta T. Okay, now delta T, obviously it would be the positive delta T, so it would be T2 minus T1. And now work done in D2A. So D2A is a isobaric process, pressure is constant. So when pressure is constant, work done is P delta V. So let us write down P, as we know that P is same at D and A, and in this complete process pressure is same. So let us write down the pressure at point D. So at point D, pressure would be equal to nR T1 by V1, and delta V would be equal to V2 minus V1. So this is nR T1 into V2 by V1 minus 1, and we know that V1 by T1 is equal to V2 by T2 because it is a isochoric process, in fact isobaric process. So V1 by V2 will be equal to T1 by T2 and V2 by V1 will be T2 by T1. So nR, and this is T2 by T1 minus 1 into T1. So this will be nR, work done will be nR into T2 minus T1. So if we find out the ratio of Q and W, so it would be 4. So the correct answer of this question is 4.